Okay. All right, so now that we have everything restarted, okay, so there we go. When we go to the register bank, we pick out register A, register B, and register D, and then change the radix of all of these into base 16. There we go. And then we go back to RAM and log just the last few locations. I'm pretty sure it doesn't use anything beyond 255, but just to be sure, we can start with 253, 254, 255, and change all of these to base 16 representation. And then we specify where we want the log file to be at. Okay, so this is 5.tsv. Save. Alright, so we got everything back now. We can go back to simulate and start the ticking. And it's done. Control K. And this is the last time when it stopped, right? So good thing it doesn't stop this time. Alright, so what we'll do is we're gonna create a new spreadsheet. And the first thing is I'm going to rename it so that we know what the spreadsheet is, because otherwise it's just untitled. So we'll rename it to 5log. And then from here we can just go ahead and import from the TSV file. So we're going to upload temp 5.tsv. And the one thing that is important is not to convert text to numbers, okay? Because that's the one thing that's going to mess things up, and things won't look right anymore. Is that one? I believe the rest we can just leave them the way they are. Okay, so we say import data successfully. Okay. Oh, it opens a new, becomes a new file. Okay, we'll just call it 5. Okay, that's fine. And then we can change the column size just a little bit. There we go. All right. So what are we observing? Well, we are observing that register D is initialized to 0, but you cannot see it because it starts off with a value of 0. Register A should get a value of the label. And let's see, where is that? This is register A. So by the time we get to location, well, the PC is reporting location 4, but this is actually corresponding to the instruction at location 3. We are putting RETL1 into register A. So when you go back to the assembler, you will see that that is corresponding to the return address. So when you go to the assemble tab, and you just look at RETL1, it has an address of 8. Okay. So are there any questions about this part? Okay, so everything is going as expected at this point. Okay, so going back to the log, which is this one here. So the next change is this one, which is very significant, because this is basically saying the location of register D, our stack pointer, is finally decremented from 0 to 255 or FF. Okay, so I'm allocating the byte and say that, okay, this is the location where we can store something now. Is that okay? So this is corresponding to the address. Okay, when you look up this address, it is 1 byte past the actual instruction. So the actual address of the instruction responsible for FF to change is location 05 or is location 04. So when we go back to the assemble tab, we look up what is at location 04. It is our decrement instruction. So that so everything is working the way it's supposed to. But when you look at the log, the next thing that is changed is this byte over here. RAM location 255, also known as FF in hexadecimal, is now 08. That is our return address. That's RETL1. Is that okay? So is that explaining, what I'm doing with the actual text way of logging it? This is the other way to show you, what's going on. Okay. All right. So where is the subroutine? When are we branching into the subroutine? So when you look into the program, okay, let's go back to the Assemble tab. The subroutine starts with a label of 5. Okay, it is at the address of 9. Okay, 09 is the location of the subroutine. So when you look at the log, you look at the program counter. When does it switch to 9? It's from 7 to 9. That's our unconditional branch to the subroutine. This is where it starts the execution in the subroutine itself. Is that okay? So the first thing it does in the subroutine is to say, oh, I want to return value of 5. And guess what happens? Register A got changed to 5 because of the LDI instruction. Okay? And then the next thing we're going to do is to say, I'm done. This subroutine is done. Where am I supposed to get back to? It has to get back to location 09, not 08. Okay? So, excuse me, yeah, you're correct. It has to go back to location 08 to continue execution in the caller. But how does it know that? Well, it knows it because I pushed the return address on the stack. So that's why it uses the register D, which is our stack pointer, to go to location 255 and say, okay, copy this into register B. Register B now has 08. And then it increments the stack pointer to quote unquote deallocate a byte that was used to store the return address. Now that I have used it, it doesn't have to be on the stack anymore. It can be deallocated. So that's why the stack pointer went from FF back to 00 because of the increment. Is that okay? So after that, we have the Jmp instruction. Yep.
So basically the stack, the increment, that's not important in this program. It's for when you're like making a larger program and you need to move the pointer again. Is that correct?
Okay.
It's not going to do anything if you don't.
If your program only calls one subroutine and exactly once, yes, not having that increment is not going to break anything. But most programs do not do that, right? Most programs is going to call something more than once, or it's going to call more than one things. That is when, if you forget the increment, it's going to mess up the stack. Your stack is not balanced anymore. Okay. So continuing the trace, see how this is going from 0E to 08? How did that happen? It has to be some kind of a branch instruction, right? It has to be kind of unconditional because we do not have any conditional branch in this entire program. So this happens because at location 0E, I should say 0D, we have the Jmp B instruction. We're copying register B into the program counter, and as a result, we directly tell the processor to continue execution at 08. That is the returning from the subroutine back to the caller. So is this helping, to demonstrate what is going on with that program? The good thing about, Google Document is when my computer crashes, it kept the source code here. So it's the same program that we have been working on. This is the actual source code, and the other part was the trace. The trace, by the way, is now on the Google Drive as well, so you guys can actually open it and look at it, or make a copy of that and then annotate, what's going on, on each line. So are we okay so far with just calling and returning? That's basically what the previous lab was about. Okay. So now we're going to add a few more things to it. Okay, we just specified, we just talked about how to specify a return value just by putting that value into register A. So the next thing we want to do is to say, okay, how do we pass parameters into a subroutine? Because if you can only write code in C and C++ where you cannot use parameters, that's really limiting. I mean, you can. I mean, there are ways to write programs with subroutines but without any means of passing parameters, you have to use global variables for everything, right? And that's not a very good idea. So how do we pass parameters? That's the next question. So switching back to the slides here, to pass parameters is over here. How do we pass parameters and how do we deal with local variables? This particular module is a little bit longer because the concept is a little bit more complex. Okay. So it starts with something like this, okay? Subtract 5, 3. So we want to know what is the caller, from the caller's perspective, how is this called? I'm not even trying to use the return value here. I am just trying to figure out how do we pass parameters and how do we call the subroutine. I'm not even caring whether subtract is returning a value or not. Is that okay? The way we pass parameters is the last parameter is pushed first. So based on the way we organize the stack, what is the relationship between the second parameter versus the first parameter? Which one has the higher address? The second one has the higher address. Okay, very good. Because the stack begins at a high location. As we push items, the stack pointer gets lower and lower. So whatever you push first is going to have a higher address compared to whatever you push after that. Is that okay? But this code is pretty clear about that too, because the 5, which is corresponding to the argument of 5, is stored on stack with this st instruction. And then after this, we decrement d again to store the 3. So just by looking at these 6 lines of code, we know that the 5, the argument of 5, is stored on the stack with a higher memory address compared to the argument of 3, which is right next to it, but is below it. Is that okay? So does that sound kind of awkward to you, that we are pushing the last parameter first? Sort of? No? Because it seems like we should follow the order of the parameters, and the first parameter should be pushed first. So, but there's a reason behind this. Does anyone know the reason or the rationale behind making sure that the first parameter has the lowest address? Well, not necessarily. I mean, the order of using your parameters has very little to do with the positioning of the parameters. So that may not be the case. Anyone else? Okay, so let me see if you guys know about this about C and C++. It's a very obscure feature, but it is also very useful. Okay. Do you guys know that you can write a subroutine like this? Let's see. I'm just going to put n here. Okay, first of all, this is legitimate syntactically correct function definition. In other words, dot 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 is actually correct. Okay, it means that the sum has at least one parameter, but it can have any parameter greater than 1. So now the question is, how do we access all those additional parameters? Is that okay? Yep. Yes, it will work in C++ as well. Okay. So let's say the way we use sum is like this. Okay, so let's say this is your main, and in your main you have variable x, and x is the sum of 1, 5, 2, 10, and then the 0. So the 0 is a null terminator. So by the time we get to the 0, we know that we have summed up all the terms. Is that okay? So now the question is, from here, how do I know how to get to the 5? Because I know how to get to the 1. It's the first parameter. How do we get to the 5, which is the next parameter? And then after the 5, there's the 2. After the 2, there's the 10. And then after the 10, there's a 0, which is when I say, oh, okay, we're done. But how do we do this? Go ahead. Oh, I thought you had a, yep, yep. So we are relying on that. So the implementation of this code is we need a pointer to an integer. So we have a pointer that is initialized to the address of n itself. So this is the address of a parameter. And then the loop is going to say as long as whatever PTR points to is non-zero, we're going to do the following. We also need a sum, a temporary variable for the sum. So I'm just going to call that result. Okay. So result is initialized to 0 to begin with. Okay. So if there's nothing here or n itself is 0, we just say we're done, nothing to do. Okay. So if PTR is non-zero, the first thing we do is we say result plus equal to whatever PTR points to, because that's an integer that I want to actually make use of. And then here's the fun part. The fun part is the next statement is just incrementing the pointer. In other words, I'm assuming that there are additional arguments after whatever PTR points to. And I keep scanning forward until I find that 0, which is a null terminator, then I stop. Is that okay or not? Yep. Yeah, the 0 is an indicator of when I should stop. Yep. It's a null terminator, basically. It serves the same purpose as a null terminator, except this 0 is not a char, it is an int. Are there any questions about this code? Any particular construct here that is unfamiliar to you? Yep. Okay, which line are we talking about? Are we talking about this line or this line? This one? Okay, so the question is, what does it do? What is a plus equal to? Huh? Say that one more time. Why would it equal to 5? There's no 5 in here. So the first thing that PTR points to is the first argument. So it would be 1, and then PTR points to the 5, and then PTR points to 2, and then PTR points to 10, and then PTR points to 0. But at that point, the loop is going to exit because it doesn't meet the requirement to stay in the loop anymore. Is that okay? This is the reason why we have to push the last parameter first, so that the argument of 0 has the highest address, the argument of 10 has the second highest address, and goes all the way back so that the 1, which is argument 1, has the lowest address, because I can only know the address of the first argument, but I can assume the other arguments are after that. So this is the reason why we have to push the arguments backwards. You push the last argument first so that the last argument always end up having the highest address. Now, I could have just said that that's the way things are done without explaining why, but I found that this is actually useful sometimes. I mean, you might have learned something that you did not know about C or C++. But this is also the reason why we have to push the last argument first, and why it's not arbitrary and go like, can we push the first argument first and push the last argument last? No, not in C and C++. Okay, so are we good so far? So now, getting back to this note here, the call to subtract has 5 as the second argument and 3 as the first argument. So that's why we have to push 5 first, and then we push the 3, and then we push the return address, and then we can call the subroutine, or we can continue execution in the subroutine. The subroutine is responsible to come back to this particular label by making use of the stack, because the return address is on the stack. And then the subroutine uses the return address on the stack to get back to this point. But the caller has got one more thing to do. It has to deallocate the space used by the two arguments. That is the responsibility of the caller. Are we doing okay so far with this code? Maybe, sort of. Yep.
So it doesn't actually subtract, it just kind of puts the
I just called a subroutine. I don't know what the subroutine is going to do. Even though it's called subtract, we don't know what it's going to do. I don't even know whether it's returning a value or not. So at this point, I don't know. But the only thing I really want to know at this point is how do I call the subroutine? How do I push the arguments on the stack? How do I pass control to the subroutine? And how do I clean up the stack after the subroutine returns? Is that okay or not? If it's not okay, tell me which part of it is not clicking. Okay, silence.
D is the pointer, correct?
D is the stack pointer.
Yeah.
Register D is the stack pointer. So basically, you want to look at the instructions as a bunch. So these three instructions together is pushing 5 on the stack. These three as a bunch is pushing 3 on the stack. So they are responsible for pushing the arguments on the stack. These three are pushing the return address on the stack, so that the subroutine knows where to get back to. And then this instruction is continuing execution at the subroutine, so that the subroutine can start execution. But when the subroutine ends, it needs to go to the stack to retrieve the return address so that it can get back to this point. So that it will be returning back to the caller. When we are back to the caller itself is responsible to deallocate the 2 bytes used for the arguments. Remember the 5 and the 2? The first increment D is going to deallocate the space used by the 3, and then the second increment is going to reclaim the space used by the 5.
Because the 5 is last, it was pushed first.
The 5 was pushed first, and that's why it is reclaimed last. Yep. Is that okay? So now the question is, from the perspective of subtract as a subroutine, what does the stack look like at the entry point of subtract? That's the next question. So the subroutine, okay, so I want to implement subtract like this. Is that surprising to you? That subtract is, this is the C code corresponding to the subroutine called subtract? It surprised you? No? Okay. I'm hoping that it does not surprise anyone. Okay, so now the question is, how do we do this in assembly? Now, we know one thing already. We know a few things already. We know that X has a lower address, Y has a higher address. We know that. We also know whatever X minus Y is, we have to put it into register A. We also know that when this is all done, we need to go to the stack to retrieve the return address and use that so that we can go back to the caller to continue execution in the caller. So we know all of those components already. The one thing that we do not know is how do we get to parameter X and how do we get to parameter Y? That is the missing piece, right? So what we need to do now is to look at this code and figure out what is the stack going to look like. And then from the perspective of the callee, we want to know, okay, from its perspective, what is going on the stack, and how do we get to parameter X and parameter Y? Is that okay? All right. Okay, so with this one, it might be better for me to use the tablet so that we can actually show what is in memory. It's going to be a little bit difficult to show because the content on the stack changes. Okay, where the stack pointer points to changes from one instruction to another instruction. So this is going to be a little bit difficult to display, but I will try my best. And devices. Okay. There we go. Okay. All right. So the way we're going to do this is to look at this from the perspective of the callee. In other words, I want to be able to draw the stack as much as possible. So what we'll do is we're going to say this line is basically the line before this chunk of code. So this chunk of space on the stack is already used by the time we execute the caller's code. In other words, that chunk of space is already used by the time we get to the caller's code, which is right here. Is that okay as an assumption that some portion of the stack is already in use by the time we get here? Okay. All right. So given that assumption, what is this going to do to the stack? It's pushing 5 on the stack. So from the perspective of this picture, where's 5 going to go on the stack? It's going to go right below the portion that was used, prior to this code. Is that okay? Going back to this code here, the next thing we're going to push is the 3. So these 3 instructions together is going to push the 3. So the stack is going to look like this after those 3 instructions. Is that okay? I'm assuming that each row is 1 byte. So there's 1 byte that stores the value of 5. There's another byte that stores the value of 3. What is next? The return address. So the return address is also pushed on the stack using these 3 instructions. So from the stack perspective, now we have the return address pushed on the stack. And it is in this particular order too, because that is dictated by the sequence of pushing. Whatever you push first has the highest address. Whatever you push last has the lowest address. Is that okay? Yes? No? Sorry. Okay, good. All right. So at this point, okay, going back to the code, we continue execution in the subroutine. So from the subroutine's perspective, it knows that register D is pointing to the return address. And that's the only thing that it can assume. The only thing the subroutine can assume, any subroutine can assume, is the stack pointer is pointing to a return address. Is that okay? So now going into the subroutine code, okay, so I'm jumping around a little bit because the continuation is right here. The first thing is a CPR instruction. What does it do? I mean, the comment pretty much spells out everything. CPR, by the way, stands for copy register. So register C now has the same content as register D, which is basically saying, oh, okay, that's easy to display, because now we can say that, oh, by the way, register C is also pointing to the same location. Is that okay? Because they're the same. If register D is pointing to the return address, so is register C. The next instruction is just adding 1 to C, okay, which is the same thing as increment. What is that going to do now? Register C is no longer pointing to the same thing that register D is. Register C is now pointing to 1 byte above whatever register D is pointing to. Register D is still pointing to the return address. I didn't mess around with register D. What do you think register C is pointing to now? The 3, the argument of 3. Very good. Okay. So finally we're getting somewhere, right? So register C is now pointing to the 3 on the stack. In other words, register C now has the address of the first parameter. Switching back to this code, and since register C is the address of something, what do you think I'm going to do with it? Register C, okay, let me say that one more time. Register C is the address of something. I'm going to dereference it. That's the only way to use an address, right? Or one of the very few ways to use an address. So I'm going to dereference C, which has the address of the first parameter. And what does that get me? The content, okay? The actual value of the first parameter. So register A, after line 5, now has the value of the first parameter. Not the address of. Register C has the address of that. But register A has the value of the first parameter. Is that okay? What about the next instruction? Oh, the next instruction is an increment, and we are incrementing C. Right before this, where was C pointing to again? The 3. What is above the 3? Right above? The 5. Okay? So from the picture perspective, now I'm saying, oh, by the way, register C is incremented again, so that it now points to the 5, which is the second parameter. Okay? And what am I going to do? After I increment C, I load it into B. I load indirect, so that whatever C is pointing to, the value of the location that it points to, is now stored in register B. And what is that? 5, right? So register A has 3 at this point. Register B has 5 at this point. What was I supposed to do with these two things? I mean, it's kind of spelled out as the next instruction. Subtract, very good. Okay, so we're supposed to subtract the second parameter from the first. B has the value of the second parameter. A has the value of the first parameter. So that's why we are doing the subtraction, like sub AB. And then I have to make sure that this value is now stored in register A, because by convention, register A returns the value of a subroutine. So technically speaking, I should use CPRAA, right? I need to copy register A to register A. Does that make sense to you? It's not supposed to. Register A already has the value, the return value. I don't have to do a single thing. The correct return value is in register A already. I'm done with the return value thing. Is that okay? What is the next instruction going to do? Okay, like this one here. What is register D pointing to all this time? The return address. Very good. So if you go back to the picture, okay, right here, register D has never changed. It has always been pointing to the one thing, which is the return address. So in the code, in the execution, at this time, I'm just going to dereference whatever D is pointing to and then copy that to register B. But according to the stack picture, register D was pointing to the return address. So now I'm retrieving the return address and put it into register B. So register B is now the return address. Then we increment D. Okay, so what happens when you increment D in the picture? D is no longer pointing here. D is now pointing here. Going back to this code, and then the next thing we do is we're branching based on whatever we have in register B. Tell me again what is in register B. The return address. So we are now continuing. So this jump instruction, JMP but not JMP I instruction, is going to continue execution to the return address. Is that okay? So from the perspective of tracing this code, now we are back to this point. Is that okay? So what do we do at this point? What does the stack look like at this point? The stack looks like this. Okay. Do I still need the 5 or the 3 on the stack at this point? The subroutine is all done. It has just returned with a proper return value. I don't need the 5 or nor the 3 on the stack. So that's why I need to bump register D up twice. So the register D goes back to point to whatever the thing it was pointing to before this entire chunk of code. Is that okay? So this is kind of like the more dynamic way of kind of showing what's happening when you execute a code. You can probably get the same kind of information by logging, in the simulator and looking at the log. But this is just, a better way to kind of talk about it. All right. Are there any questions about this part of the module? What the caller has to do, what the subroutine has to do, and what the stack looks like at the time that the subroutine has control, and also what the caller has to do again after the subroutine returns back to the caller. So are there any questions about this entire sequence? No questions? Yep. In the subroutine, yep. So in the subroutine, this is the instruction that loads the return address into register B. Why do I do that? Because what are you going to do at the end of a subroutine? And how do you know where to go back to? What address are you talking about? No, register D is a stack pointer. It points to the return address. Okay, yep. Yep, you could use C2. Yep, I'm just using whatever register is next to A. I cannot use A because register A is already used to specify the return value, so I cannot mess around with register A. But I could have used register C, yes. So register B or C can be used in this context.
So what's the difference between the JMPI and the JMP? Then I should use both of them in this situation, right?
No, one only uses a register. JMP uses a register as the argument or the operand. JMPI uses an immediate operand. So JMPI in this case uses an immediate operand, which usually is a label.
Oh, okay.
So basically one is a constant, the other one is much more flexible and say that whatever is in this register, that's where we're going.
What's an immediate operand?
An immediate operand is basically a constant. So whatever you specify next to the mnemonic of the instruction is just going to be that. In other words, if you look at line 10, the only place it can go to is the label subtract. It can never go to some place other than the label subtract. But when you look at JMPB, it depends on what register B has at the time. If register B has a value of 20 in hexadecimal, it will continue execution at 20 in RAM. If register B has a value of, let's say, 45 in hexadecimal, JMPB is going to go continue execution at location 45. So JMPB is far more flexible compared to the JMPI instruction. But if I do not support JMPI, it's going to be really tedious to do any type of branching because you have to load a register with where you want to branch to before you actually do the branching. So that's a lot more tedious. And that's why I support the JMPI instruction so that we don't have to do all that tedious stuff. All right. Are we good at this point? So we know what a parameter is, where it is on stack. Yep. Mm-hmm.
Okay, so where it says sub AB, can't you just do sub A parentheses C? Or do you have to load C?
You mean this subtract instruction here?
Yeah, why did you have to load C? Can't you just do parentheses C instead of B?
Okay, so instead of asking why can't I do that, let me ask you the reverse of that question. Why can I do the SUB A and then in parentheses C? Okay. First of all, let's check out a few things. Okay, so we'll check out the assembler. Okay, the assembler is the first thing that I'm going to check and say, is the assembler going to have a problem with that? Okay, subtract A in parentheses C. and it says we need a single register without the parentheses. So it's not really supported because what opcode corresponds to subtract? What family of opcodes is supported by subtract or implement subtract? We go to the opcodes table, right? So the opcodes table is right here, and we look up subtract. So subtract is
001.
So we go down here, and subtract is right here. There we go. Is that okay? So this really defines what opcode we can use with subtract. So with subtract, the syntax is you have to specify 2 registers and cannot use parentheses around it. Okay? But now the question is, why can't we dereference YY? Why do we have to just use whatever value YY is specifying? Where do you think we're going to go next? The microcode. The microcode dictates what this particular opcode is going to do. Okay? So where do we find the microcode, or in a way that we can actually read? We go to the processor folder, we go to the opcodes folder, and then we look at subtract sub.c. And over here, if you look at these pathways, nothing here is going to turn on RAM. Okay, let's do some counting. Let's double check, make sure. Okay, so we're going to split the screen, and the top one is going to go to ucode.c. There we go. All right. So the RAM components, or the RAM control signals, are the last, the second to the last and the third to the last items. And then when you look into the slides, this particular microcode slides, does it use RAM at all? Does not seem like it, because IREN, or instruction register enable, is the very last one. RAM select is the second last one. That's a 0. I am not using RAM at all. So there's no way the subtract instruction can do any type of dereferencing, because it doesn't even turn on the RAM component. So is that answering your question? Because the reason why you ask the question is because you are thinking in syntax. Okay, if we put parentheses around something, we're dereferencing. But the problem is the syntax is determined after we specify the microcode, and the microcode is dictating what we can and cannot do with each instruction. So we cannot just say, oh, by convention, putting parentheses around the register is dereferencing the register, so we can use that anytime we need it. It doesn't work that way. And for the same reason, we also cannot say SUB A with a constant with an immediate, because that is also not supported by the microcode. The microcode is saying that we can only use a register to go to the input 1 of the ALU. We can only use another register, possibly another register, to go to input 2 of the ALU. And therefore, you're locked down. You have no other choice but to use just 2 registers. But that was a good question, because it reflects the thinking process, and it is not uncommon that people would think that way, because we learned that putting parentheses around something is dereferencing, and we can specify constants and labels and stuff like that. Can we mix and match those things? And the answer is no, because it is it's not like C, where you can combine things in a different way. This one is far more restrictive. Yep.
So kind of to summarize, referencing and dereferencing is always its own step. You can't combine
The
them.
only 2 instructions that can dereference is LD and ST. LD is for reading from RAM, ST is for storing into RAM. Those are the only 2 instructions that can actually do any type of dereferencing. And all the arithmetic operations, like add, subtract, bitwise not, bitwise and, bitwise or, and right shift, they can only work with registers directly. Okay, and in the jump instructions, there are 2 different mnemonics, and that's why JMP is one mnemonic, and JMP without the I is another mnemonic, because each one is representing a unique family of operations. JMPI says whatever you specify has to be a constant, and every single time you execute this instruction, it's always going to that location. JMP without the I specifies a register, and it has to be one of the 4 registers. You cannot change which register you're using, but whatever the value of the register is at the time you execute that instruction will determine where you're going to go when you execute the instruction. So everything boils down to the microcode. So that's why, when you have a question, like what you had a little bit earlier, you basically have to look at the microcode corresponding to the mnemonic of SUB or subtract. SUB is nothing more than a mnemonic, a quick way so that we can remember what instruction we need to use, so that we don't have to refer back to the binary code of 1001 XXYY. That's the reason why we have SUB or subtract as a mnemonic. Okay? But what it can and cannot do is completely dictated by the microcode that is underlying the instruction. Is that okay? So that's a good question, because what I need to do. Okay, come on, recognize my fingerprint. Okay, there we go. Okay, so getting back to here. Okay, so we have to distinguish the several things. So we got opcodes, okay? So the opcode is referring to these bit patterns, okay? So focusing on just subtract 1001 XXYY is the opcode, okay? So 1001 XXYY is the opcode. This is the bit pattern that you have to put into RAM as instructions, so that the processor can quote unquote execute those instructions, okay? In one direction, the opcode is implemented by microcode. Okay, so the microcode has 2 representations. The first representation is over here as locations in ROM. That is microcode. Okay, so when you look at the microcode at 9 blah 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 0, those are the microcode for the subtract instruction. So let me show you exactly what I mean by that. So when you go to 9 blah blah, okay, so 900 is subtracting A from A, 910 is subtracting B from A, and so on and so forth. This is a pretty difficult way to look at microcode, because you have to quote unquote decompress the hexadecimal digits into binary digits and then figure out the position and all that stuff. So the other way to visualize the microcode is to look at this code here, okay? Because it's broken up into individual pieces for you already, and these are the names corresponding to those particular tunnels. So that's the easier way to understand what is each microcode going to do to the processor. Yep. Huh? It's in the opcodes zip file. So download the opcodes.zip file and unzip it, and all of these source files should be there. Okay. But just to complete the whole picture, because that's the point here. Okay. Okay. So beneath the microcode, okay, I need to insert something over here. So beneath the microcode basically are controlling the control signals of the individual components. So beneath this is the processor architecture. So in this direction, we're going to basically lower level constructs or lower level concepts. So you don't want to program you don't want to write your code using 1001 and then figure out what is XX and what is YY. So that's why we have mnemonics. MNE mnemonics. Okay, so the mnemonics is this is SUB XY. Is that okay? So at the very lowest possible level is what we see in Logic Sim, which is the processor architecture. And all the control lines that goes to all the multiplexers, demultiplexers, registers, RAM, and so on and so forth. Okay, that's the very lowest level of definitions. Okay, it doesn't get any lower than that. How we can coordinate all of those components to work together has to do with the microcode. And the microcode resides in ROM. So when you look into the ROM, you can see the microcode. But just being able to see the microcode as hexadecimal numbers doesn't really help you understand what it does. So that's why you have to look at the source code in C to easily figure out, okay, this is controlling this is controlling that, and so on. The microcode is underlying the opcode. So every time in the fetch cycle of executing an instruction, the opcode is put into the instruction register. In the decode cycle, the opcode combined with 4 zeros, padding 4 zeros to the least significant side, is what becomes the microcode pointer. Okay, that's the relationship between microcode and opcode. Opcode indexes into the microcode in ROM. Opcode is what you store in RAM. Okay. But opcode is binary, okay? It's 1001 XXYY. Figure out what is your register X and what is your register Y, and then you can come up with the actual content of that byte. It is not convenient. And that's why we have mnemonics, so that the assembler can take your instructions using the mnemonic and figure out how to convert your XY, which is ABCD, into the opcode that is stored in RAM. It keeps track of all the locations, so you can use symbolic name for the labels, so that you don't have to count. Okay, where am I going to go back to? Count from the beginning, 1, 2, 3, 4, 5, 6, 7, 8, 9 bytes. The assembler, which is a spreadsheet, takes care of that for you. So is that helpful? Because I think that's basically why we have that question to begin with. In other words, in addition to answering your question, I'm questioning why you're asking that question and answer that question as well. The second derivative, so to speak. Are we good so far? Because I think that's one concept that we have to clarify, because we have all of these things. How do they stack up? No pun intended. And that's the picture that we saw earlier is basically how they quote unquote stack up. Let me display that one more time. So this is kind of an important table, important picture. We start everything with the architecture of the processor, microcode, opcode, and then mnemonic. All right, so we got 2 minutes for me to clean up here and then move over to the lab. So I'll see you guys over at the lab. Let me stop the stop OBS first.